All right. Good morning, everybody. Wait. Ano bang tama pag 12 noon na? Good morning or good afternoon na? I'm not sure, but anyway, good morning or good afternoon, everyone. So last time we finished module 2 finally after I think one day delay. All right. So now we'll start a brand new module. So it's going to be module number 3. So it's already available in Canvas, I think, since last week. So ito yung itatry nating simulan ngayon and then tapusin next week. So that means probably laboratory exercise 1.2, which comes with this module, will be a little bit adjusted para mabawasan kasi hindi natin matatapos yung buo niyang coverage. But, and also since we didn't finish module number 2 last week, meron pang naiwan na portion ng laboratory exercise 1.1 for next week, all right? So that means on Monday, you need to do laboratory exercise 1.1 part B and some parts of laboratory exercise 1.2 depending on what we'll finish today, all right? So, sana clear yon. So, dalawa yung isa-submit nyo on Monday. Pero maiksi lang naman sila parehas, right? So, pero magkahiwalay na PDFs yung kailangan ko. All right? So, it's almost the weekend before we rest. All right? So, let's end the week with a big bang. All right? Talking some more maths. So, today we'll talk about some iterative schemes in root finding. So, last time, pinag-aralan natin yung bisection method saka yung regular false method. And there are interval methods because we are iterating on the intervals. So we start with a big enough interval so that we know that there exists a root, and we use the IVT to invoke or to guarantee the existence of a root. All right. Tapos at every step of the method, we are shortening the interval. Pinapaiksi natin ng pinapaiksi yung interval so that up to some point, we are very, very close to the root, right? Meaning that the interval is very, very short already. Or we have met the function value tolerance. So yun yung yun yung approach natin last time. So sa interval tayo nagbabase, tapos pumipili tayo ng isang member ng interval to be our estimate. Now, those two methods always converge. Guaranteed na lagi nagko-converge yung bisection at regular falsi. The bisection method converges linearly, all right, with asymptotic error constant of 1. And we said that the regular falsi method will depend on the function you're considering, because if you're considering a function that is convex down or a function that has a steep rate of growth or decay, all right, so posibleng mas mabagal yung convergence ng regular falsi method. And then some mathematicians try to address that problem with the regular falsi method na ang hirap i-analyze in general ano yung order of convergence, so ano yung rate of convergence ng method. Nagbigay sila ng modifications, and the most popular ones are the Illinois type modifications. So yung Illinois algorithm, the very basic Illinois algorithm, takes half of the function value of the retained endpoint. Tapos doon niya dinodraw yung line, nakukunan niya ng x-intercept, which is fine because doing so made the convergence super linear. So yung rate of convergence niya na, if I'm not mistaken, is around 1.442. And then I need to make some correction. I think last time I referred to this number to be something like the golden ratio. Hindi nga pala siya yung golden ratio. Yung golden ratio ay 1.618 dot dot dot. All right, so it's a little bit below the golden ratio. So ang order of convergence sa mga modified regular false methods ay is greater than 1. Okay, so a little bit faster than the bisection method. But even though we were able to push the rate of convergence to 1.442, it's still spectacularly slow. All right, medyo mabagal pa rin. It will take you a considerable number of iterations, especially if you started with a very long interval. All right, or if you're dealing with a very crazy function for the case of the classical regular falsi method. Now, people might argue that that's not a big problem nowadays because we have supercomputers which can do millions of calculations per second, all right? Which is true. Kaya hindi na tayo ganun ka picky with the root finding techniques. Even people are still using the modified regular falsi, even though subquadratic, below quadratic convergence yung rate niya. Kasi nga mabibilis na yung computers natin. So, but there's still a drawback there. Kung root finding lang, that's fine. Pero if your root finding routine is part of a bigger program and it needs to be called thousands or hundreds of thousands of times in your program, okay? Or gagamitin mo siya to simultaneously compute the roots of, say, uh, 100 nonlinear functions that you need in your calculations, then it might be difficult. Magko-compound na yung bagal ng mga methods na to, right? So if it's part of a routine, then it might be better to look for faster methods, okay? So isa yon sa mga drawback ng interval methods. The other drawback is hindi tayo nakakakuha ng multiple routes. Okay? So isang route at a time lamang yung nakukuha natin because that's the way the method is designed, right? Sa bisection method, actually, hindi natin tinitingnan yung function value sa pag-compute ng approximate. Ginagamit lang natin yung function values o yung behavior ni f sa pagpili ng interval na gagamitin. Alright? But it doesn't play a role in selecting the route. So ibig sabihin talagang design siya na pipili lang ng isang number on a very small interval that contains a root. Okay, so isa lang talaga yung makukuha natin by design. And the same thing as the regular falsy method kasi nag-iterate lang naman tayo, kinukuha mo yung x-intercept which will drive closer and closer to the root. Okay? If you want to use these methods and you want to get a different root, then you need to alter the choice of interval to begin with. All right? So palitan mo yung interval, piliin mo yung interval na maglalaman ng hinahanap mong root. Kaya lang wala tayong way para makuha in one iteration or in one go of the process yung mga multiple roots. Excuse me, guys. Another problem is hindi naka-capture ng mga interval-based methods yung complex roots. All right, so there are some functions that will have complex numbers as their roots. Tapos, usually in some applications like in acoustics and electromagnetics, even in solving ODEs, mahalaga yung mga complex roots. All right? Yung mga methods by design, and you will imagine this kasi nakatingin tayo sa interval. So, dun sa interval, wala namang complex number or wala namang complex number na may non-zero imaginary part na member. So, ibig sabihin, imposible talaga na makuha niya yung mga complex roots. Okay? So these are the things that we will try to address in the next few methods that we will discuss, all right? Primarily, we will begin with addressing the slow convergence of these methods. And for that, we will introduce some more iterative methods, okay? Ang title ng section, iterative methods, pero yung bisection sa regular fallacy, iterative din sila kasi to go to the next process, you will use previous results, okay? Tapos, ngayon, hindi tayo magbe-base sa interval. Iterative pa rin, pero hindi interval yung input. Initial guess lang. Isang guess para dun sa root yung magiging input ng algorithms. And then from there, we will generate a sequence of approximates that will hopefully converge to the actual root. All right? Now, Chazelle has a nice question. Thank you, Chazelle, for asking this. Saan nanggagaling yung C sub 0 sa mga modifications ng regular fallacy? That's a nice question, all right? Nakalimutan ko pala itong banggitin last time. Remember, dun sa modified regular fallacy, binabago natin yung function value na ginagamit dun sa pagkuha ng root. Yung C sub 0, yung kauna-una ang approximate, pwede nyo siyang kunin mula dun sa regular application ng regular fallacy. So remember, oops. To si A, ito si B. All right? So, tawagin natin A sub 0, B sub 0. Unang iteration. So, magkaiba yung sign. So, dun sa mga modifications ng regular fallacy, pwede nyo munang ipagawa yung regular fallacy method on the first step. All right? So, ibig sabihin yung C sub 0 natin, yung x-intercept ng line passing through A sub 0 and B sub 0. So, you can use this as your C sub 0. Okay? And then kung kung Anderson Bjork yung modification, then kailangan natin kunin yung function value ni C sub 0. Okay, so ito yung f of C sub 0. Dahil negative si f of C sub 0, ang gagawin natin si A1 ay magiging si A sub 0 pa rin. So ang na-retain ay si A1. Tapos, ito na yung magiging B1 natin. So ito yung magiging, oops, what happened? Okay. This will be our B1. Okay. Tapos, dun sa susunod na iteration, dahil modified na yung regular fallacy method, instead of joining the line starting from this point, papunta sa point na to, sa Anderson-Bjork, kukomputin nyo yung 1 minus f prime, anong numerator? C sub n minus 1 over f prime of b sub n minus 1, yung hindi na-retain. Kung ito ay positive, ito yung value ni m. Kung ito ay negative, 1/2 yung multiplier. Alright? So, m equals this 1/2 if this is positive. Tapos ito ay if otherwise. Tama ba guys? Ito yung formula nung sa m. Please correct me if I'm wrong. Alright. So, ibig sabihin, ito yung mamumultiply. So, mamumultiply siya ng m times f of a sub 1. Tapos, ito yung i-connect natin. Okay? So, this would be our c sub 1 for the Anderson-Bjork algorithm. Okay? Tapos, tingnan nyo yung mangyayari. Kung hindi ko ginawa yung modification, ito sana yung magiging approximate ko. I-join ko lang yung dalawa, no? Ito sana yung C sub 1 dun sa hindi pa modified na regular fallacy. Pero dun sa modified regular fallacy, mas malapit na tayo dun sa actual root na hinahanap. Okay? Excuse me guys again. Yeah, thank you Michael. Wala nga prime to. Bakit nagka-derivative? Thank you. Nice catch. So that's F and F. All right. Yun din siguro yung sinasabi ni Chazel. All right. So I think that's it. Is that clear? So you can make your own modification of the regular fallacy method. Pwedeng yung C sub 0, wag niyong kunin na yung C sub 0, pwede niyo nang simulan pwede niyo nang simulan yung modification. Pwedeng doon pa lang sa pagko-compute ng C sub 0, kunin niyo na yung M times F of A1 o kaya yung M times F of B. All right? Tapos pwedeng yun yung maging initial approach nyo. Pero theoretically it will still make sense, all right? And dahil first step pa lang naman, hindi siya gaanong ka-crucial. Pero ito yung suggested. Gamitin niyo yung regular fallacy dun sa first step. Tapos, saka nyo gamitin yung modifications later. Okay? So, there's already, I think, one of you who submitted laboratory exercise 1.1b. Right? D2L din yon, kaya na-checkan ko na. Parang perfect yung nakuha niya. So I don't think it's very hard, okay? Pag-isipan niyo lang yung programming talaga. Okay? All right, other questions before we proceed? Okay. Okay. So yung unang iterative method that natitingnan natin that will hopefully accelerate the convergence or meron siyang rate of convergence na mas mabilis kaysa dun sa interval-based method is what we call the Newton Raphson method. Now, the Newton Raphson method is a very popular technique, all right? Kahit yung unang appearance ng Newton Raphson ay noong 1669 pa. Hanggang ngayon, yung Newton Raphson method in the way it was presented before is still used today. All right? Ganon kaganda yung Newton Raphson method. Simple siya at mabilis yung convergence niya. Kahit ako in my researches, gumagamit pa rin ako ng Newton Raphson method pagko-compute ng isang optimization problem. All right? So Newton Raphson pa rin yung pinaka-basic, the same method proposed by Newton in 1669. And you will see that this is a very innovative method by that time kasi gumagamit siya ng derivatives. Okay? And kaka-invento pa lang ni Newton nung calculus, alright? Tapos nagamit niya kagad yung calculus to illustrate one way to speed up the usual classical root finding techniques, alright? So this was first broached in 1669, of course, by Newton kasi siya yung nag-imbento ng calculus. This is a calculus-based method, so it makes sense na siya yung unang makagawa nito. A little modification and a simpler description of the method was given by Raphson in 1690. Kaya ang tawag sa kanya ay Newton Raphson. Pero the idea behind it is really due to Newton. Si Raphson lang yung nag-polish ng presentation. Okay? Pero by that time, they were only applying it to polynomials. It was in 1740 when Thomas Simpson, who presented the method as a root finding algorithm for general nonlinear functions. And probably because by that time, in the 1740s, marami na tayong alam na bagong discoveries about calculus compared to the 1660s, nakaka-imbento pa lang niya. Alright? So this method dates back to 1740, and yet it is very useful until today. Kasi nga mabilis yung convergence ng Newton Raphson method. But of course, it will come with a price that we will see later. Okay? Now, let's first look at the idea, the theory behind the method itself. Okay? So kunwari, kukunin natin yung root ng isang function, yung blue function, f of x. Okay? It is not an interval-based method, so you don't need to have an interval and check the function values at the endpoints if they are opposite in signs. Basta alam mo lang dapat may root yung function. Okay? Now we are trying to get the root r. Okay? Ang idea nito ay, di ba dun sa regular fallacy, kinukuha natin yung line passing through yung dalawang endpoints. And we use the intercept of that line to be our estimate. So Newton Raphson method naman, gumagamit pa rin siya ng line. Kaya isa tong example ng straight line method. Kukunin niyo yung line na mag-approximate dun sa curve, and then the x-intercept of that line will serve as our estimate. And then we'll continue the process until we don't satisfy the stopping criteria. Okay? So in this case, straight line pa rin, pero ang gagamitin natin yung tangent line. So kailangan mo ng initial guess. You need an initial guess x sub 0. Ito yung una nating hula para dun sa root. Okay? Take the function value of x sub 0, draw the tangent line to the curve of f passing through x sub 0, comma, f of x sub 0. So itong orange na nakikita nyo dyan, siya yung tangent line. And remember, yung slope ng tangent line na yan, yung derivative ng function. Okay? Kaya ito ay calculus-based. Alright? So hindi to may invento before 1600s kasi kaka-invento pa lang ng calculus ng 1600s. Right? So yeah, kukunin mo yung function, kukunin mo yung tangent line passing through your initial guess, all right? And then the x-intercept of that line will serve as our estimate x sub 1, our new estimate x sub 1, right? And then we will continue the process. So ganun ulit. Kunin ko yung f of x sub 1, andito siya. Tapos kunin ko yung tangent line passing through x1, comma, f of x sub 1. Ito yung tangent line na yon. Okay? So, yung tangent line na yan, kukunin ko yung x-intercept. This would be my x sub 2. And then you continue the process. And you see in this nice illustration na napakabilis talaga ng convergence, no? Ang bilis ng jump. Starting from x1, mukhang palapit na palapit talaga ako dun sa actual root r. And that's it. That's the simple description of Newton's method or the Newton Raphson method. Okay? So does the idea make sense, or does this plan make sense? Kasi susunod natin gagawin, i-derive natin paano natin to i-implement. But graphically, this is the Newton Raphson method. Isipin nyo, ano talaga, naunahan lang tayo ni Newton imbentohin to kasi this method really makes sense, right? Tapos, pina-follow niya yung contour ng graph. So basically, nag-a-adjust yung line na kino-consider natin dun sa behavior ng function, right? If your function is very steep, then the tangent line will also be very steep. If your function, if the curve is convex down, then your function will adjust a little bit. Nako-consider niya talaga yung curvature ng function as you go along. Okay? All right, so no questions? Is everything clear? Okay, now let's plan on deriving the formula, how to get the series or the sequence of approximates x sub i's, all right? So ang idea, kukunin mo lang yung equation nung line na nung tangent line actually, right? So what's the equation of the orange line here? The orange line has equation, ay generalize na lang natin, gawin na lang natin x sub n na tayo para makuha natin yung formula, right? So we need to find the equation of the orange line. But the orange line is the tangent line passing through x sub n, comma, f of x sub n. All right? So ito yung point na yan, kukunin natin yung tangent line. And the simple formula from elementary algebra tells us this is y minus f of x sub n equals the slope of the line, but the slope of the line is the derivative of x sub n, right? Kaya dito pumasok yung konsepto ng calculus, the derivative as the slope of the tangent line, times x minus x sub n. All right, si x sub n yung current estimate natin. We are looking for how to get x sub n plus 1. But remember, x sub n plus 1 is the x-intercept of this line. All right, so we need to find the x-intercept. To find the x-intercept, all right, so the x-intercept would be x sub n plus 1 comma 0. All right, siya yung x-intercept nitong tangent line na ito. X sub n plus 1 kasi kung ano man yung x value na yon na magpapa-0 dun sa y, yun yung iti-treat natin as our next estimate. All right? So I'll use this info, plug that in into here, and then solve for x sub n plus 1. So we'll have negative f of x sub n equals f prime of x sub n times x sub n plus 1 minus x sub n. All right? And then again, we need to solve for x sub n plus 1. So I'll divide both sides by f prime. Okay, so yon, dinivide ko. Tapos, anong susunod? A-add ko siya, i-add ko to doon sa kabila. Okay, and this would be my x sub n plus 1. Magiging plus pala to, no? Sorry, magiging plus pala ito. All right, and then this would be a minus. All right, so basically, this is the formula for x sub n plus 1. Okay, x sub n plus 1 is the previous value x sub n minus the ratio between the function value at x sub n and the derivative. Okay? Tama ba yung pagkakaderive ko? Sana hindi nagkamali. Though nakasulat naman siya rito. Double check nga natin. Yeah, there we go. This is the formula for the Newton Raphson method. Okay? So essentially, this is how we compute x sub n. And by the looks of it, you can easily implement it in a spreadsheet. All right? Kailangan mo lang i-program paano ko computein yung function, tas mano-mano mo nang computein yung derivative para nagpa-plug in ka na lamang. And isang drag lang to ng formula kay Excel, you will get the sequence of approximates x sub n. All right? Now, you do this repetitively, okay, but you will start with x sub 0, perform this iteration until you meet the halting criteria. And of course, dalawa na lang yung pagpipilian natin sa stopping criteria kasi wala nang interval dito. So walang interval-based stopping criterion. Okay, so we only have, function value-based stopping criterion. So we stop if the function value is very close to 0. The measure of closeness is whatever epsilon you will declare in the beginning. All right. Or yung jump criteria, which is basically you are computing the relative change in your estimates. Tingnan mo kung worth it pa ba yung susunod kong iteration. Malaki pa ba yung nababago sa mga x sub n's? Pag hindi na ganun kalaki yung percent na pagbabago sa mga x sub n's, then there's no point in continuing the algorithm. So you stop with if this ratio is below epsilon na. Okay? Or of course, if you don't want to spend much time, pwede mo siyang tigilan kapag na-meet mo na yung maximum number of iterations. Okay? All right, questions? Na-visualize niyo na ba kung paano to i-implement? Salita naman kayo guys. So, bakasyon na ba ang mga nasa isip niyo? Okay, is everything okay?
Okay naman po, sir.
Okay, masyado lang madali ba yung method kaya smooth sailing? All right. I hope that's it. Okay. Now, ano yung mga problema na pwede nating ma-foresee rito? Well, una, yung pagza-zero ng derivative. All right, that will create a problem. Pagka malas-malasan mo na yung isa sa mga estimates mo pala ay relative maximum o relative minimum. Remember, pag relative max o relative mean, nagzi-zero yung derivative, right? So you will have a problem evaluating this quotient. So you cannot do anything about that. So you should pray that you won't hit any of the relative maxima or relative minima in the iteration kasi hindi mo mako-compute yung x sub n. So a remedy to that is choose another x sub 0. Okay? So that's a simpler problem which is apparent in the way equation 3.2 is written. Okay. Ang isang pang problema nito ng Newton Raphson ay hindi siya laging nagko-converge to the root. Okay? So the convergence will be dependent on the choice of x of 0. Tingnan ko nga yung script ko. Yun na ba yung susunod? Oh, hindi pa pala yung susunod ko sasabihin. Sorry, spoiler. Okay. But anyway, so yun yung method. So just watch out for the absolute extrema kasi nagzi-zero yung derivative stuff. Okay? Bago ko ituloy yung pang-spoil about the problems about the Newton Raphson method, let's look at a quick example. Okay. Ito yung same problem as what we had in module 2. We're looking for the largest root of x to the 6th minus x minus 1. And then we'll use, I think, the function value-based stopping criterion with epsilon equals 10 to the minus 6. And now we will use 1.5 as our initial guess. Okay. So luckily, we are looking for the largest root, and a simple inspection of the graph will tell us na, yeah, yung largest root ay nandito, and that is close enough to 1.5. So we don't foresee any problem with this because it is easy for the Newton Raphson method to converge whenever the initial estimate is very close to the root. Okay. Or you can picture performing the method manually. So, ito yung 2. So, nasan si 1.5? 1, 2, 3, 4, 5. So, andito siya. Ito yung 1.5. Pwede mong manu-manuhin yung Newton Raphson method. Okay. Drawing mo yung tangent line. So, ito yung x sub 1 natin. Kunin mo yung function value. Tapos, drawing mo yung tangent line. Tingnan niyo yung pagbabago ng tangent line. Ang bilis ng pagbabago ng slope ng tangent line, and that is because ang bilis din ng pagbabago ng behavior ng function. All right, and it is considered or taken into account in the Newton Raphson method. So ito na yung x sub 2 ko, right, and so on. So it seems that this will work as for this particular example kasi nga malapit yung root yung initial guess natin dun sa actual root na hinahanap natin. So there's no problem there. And if you will implement it in in MATLAB pala yung ginamit ko. Okay. It only took 6 iterations before the stopping criterion is met. So 6 na iterations. So dun nga sa pang-5, 4.7 times 10 to the minus 5 na yung wait. Ang ginamit ko pala rito ay relative jump. Sorry. Let me see. Figure 3.2, then figure 3.3. Okay, so figure 3.3, relative jump pala yung stopping criteria na ginamit ko. And actually, akala ko function value-based. Pero actually, the recommended stopping criterion for the Newton Raphson method is the relative jump. You will see later bakit relative jump yung suggested stopping criterion. Okay. So you will see that after the on the fifth iteration, mukhang malapit na yung stopping criterion. Stopping criterion is 10 to the minus 6. And we're already at 4.71 times 10 to the minus 5 on the 5th iteration. Now, on the next iteration, 10 to the minus 9 na yung relative jump. So, ibig sabihin, wala na masyadong malaking pagbabago between the 5th and the 6th estimate. So that means we don't expect a more significant change between the 6th and the 7th iteration. So titigilan ko na yung pag-iterate kasi hindi na ganun kalaki yung pagbabago dun sa mga estimates na nakukuha natin. Right? And this is fine because here, the estimate that we got is 1.1347 and so on. And the function value of this approximate root is 10 to the minus 8, which is nice and which is close enough to 0. So we say that with this indication, it seems that we were lucky that 1.5 is a nice value for x of 0. Okay, kasi magko-converge yung ating iteration kasi nga paliit ng paliit yung difference sa mga x events. So ibig sabihin, they will become closer and closer to each other. Therefore, they will be closer and closer to a common value, which will be the limit of that sequence. So it will converge for this particular example. Yun yung gustong iparating nitong figure 3.3. Okay? Now try to recreate this data using your code. Madali lang naman i-code yung Newton Raphson, all right? So try nyo tong i-recreate. If that checks out, and then it seems that you can apply your method for any other function, okay? All right, so another example, paano kapag medyo napalayo tayo? 1.5 yung x sub 0 natin kanina. Gawin naman nating x sub 0 equals 3. Ito yung initial guess. Now, if we do that, we'll get this results or this data. It will take us 10 iterations before we get a significant or an insignificant decrease or change, an insignificant change in our estimates. Medyo natagalan lang siya ng konti, but napunta pa rin siya doon. All right? Nadagdagan lang ng ilang iterations. So it took 10 iterations so that the relative difference between two consecutive estimates is less than 10 to the minus 6. Okay? Kapag ang initial guess nyong nilagay ay halimbawa negative 5, okay? Malamang magko-converge pa rin si Newton Raphson, pero dun siya magko-converge dun sa kabilang root. Dito siya malamang magko-converge dun sa negative 1 point something or sa negative 0.9 something. Alright? So that means you need to choose your x of 0 close to the intended root or to the desired root. Kung wala kang idea kung ano yung gusto mong root, di manghula ka na lang kung ano yung initial guess. Kaya lang ang problema ng Newton Raphson, hindi siya laging nagko-converge. Dapat yung x of 0 is chosen to be close enough to your actual root. Yun yung price to pay for the fast convergence. Yung interval-based methods, mabagal nga sila, pero lagi sila nagko-converge. Pero itong Newton Raphson, napakabilis niya, pero may chance na hindi siya mag-converge. So yun yung drawback. So what we'll try to do is to investigate when will the Newton Raphson method converge para magkaroon tayo ng idea paano pumili ng mga x sub zeros. Okay? Paano natin pipiliin yung initial guess. All right? But I want you guys to try some of these exercises. Try to recreate examples 1 and 2. And then after that, pwede nyo paglaruan yung code, magbigay kayo ng iba't ibang x sub zeros. And I think this is the way you can study Math 175 much better. Okay? Dahil sa lectures, konti lang talaga yung example na mapapakita ko. So, kailangan nyo talaga mag-hands-on. Magsulat kayo ng program, try nyo i-recreate yung one or two examples na binigay ko, and then you can play with the parameters given in the problem. So, baguhin yung initial estimate, and then discover for yourself ano yung mangyayari. Okay? All right, so now going back to the problem with Newton Raphson, hindi siya palagi nagko-converge. Pero meron tayong Theorem 3.1, which is basically telling us na, yeah, magko-converge yung Newton Raphson, pero dapat piliin mo si x sub 0 to be close enough to the root you're looking for. Which sounds paradoxical kasi hindi ko nga alam kung nasan yung root ko eh. So paano ako pipili ng isang x sub 0 na malapit dun sa root? Okay? But nevertheless, Theorem 3.1 tells us na lagi siya magko-converge. Pumili ka lang ng x sub 0 that is sufficiently close to to the actual root. Okay? Pero yung pa nga rin, no, napaka-paradoxical nung statement. But let's see the details of the theorem. Pero yun yung gist ng theorem na to. Now, let's see. So if your function is twice continuous, meaning itself and its first and second derivatives are continuous. Alright, tama nga ba? C kapag ka siya ay continuous. Kapag ka continuous si... Isip ko yung notation ko. Pag C upper n, continuous hanggang nth order derivative, no? So, ibig sabihin, continuous hanggang kay second derivative. So, kung meron kang f na continuous hanggang yung second derivative niya, okay? And an interval AB contains a root of f. Now, if the derivative is not equal to 0 at the root, then we are sure that there exists a delta greater than 0 such that the sequences that you will derive from implementing the Newton Raphson method will converge to R. Okay? So, sa kahit na Kapag na-satisfy niyo yung premises ng theorem, kahit ano pa si function f, lagi kang may makikita na delta, alright, greater than 0, such that if you choose your initial point x sub 0 to be within delta units away from the root, then the Newton Raphson method will always converge. Okay, yun yung ginaguarantee ng theorem na to. So, kahit ano pa yung function mo, basta twice continuous siya, tapos hindi nagzi-zero yung derivative niya dun sa root. Ibig sabihin, lagi kang may makikitang small enough window on the root, all right? Or a small enough neighborhood of the root such that if you pick any x sub 0 from that interval, from that neighborhood, then the Newton-Raphson method will converge. Unfortunately, the theorem is silent what is delta. All right, hindi niya sa atin binigay yung delta. Ang sinasabi niya lang may nag-exist na delta. And again, kahit alam mo nga si delta, may problema pa rin tayo kasi si R ay wala tayong ka-idea kung nasan siya. So parang ano talaga to, trial and error. Which is fine because mabilis naman yung Newton-Raphson method. So pag nag-try ka ng x sub 0, after a few seconds, alam mo na kung magko-converge yung method o hindi. Kasi kung hindi siya magko-converge, hindi liliit yung relative jump dun sa iterations. Hindi to mag-approach ng 0. So ang indication natin na nagko-converge siya, yung relative jumps ay mag-approach ng 0. So kung hindi siya mag-approach ng 0, so hindi niya ma-meet yung stopping criterion. So mag-run lang yung program hanggang ma-meet niya yung maximum number of iterations. Kaya maganda na ipa-display niyo yung relative jump para alam niyo na hindi siya lumiliit. Or actually, kahit exabends lang yung nakikita nyo, pag hindi papalapit sa isang value yung exabend, so napaka-crazy ng behavior ng exabends kahit naka 1,000 iterations ka na, ibig sabihin hindi convergent yung Newton-Raphson method. Okay? So you need to find another choice for x sub 0. Okay? Kasi ang sinasabi lang, ang guarantee sa Newton-Raphson, magko-converge yung method kapag ka yung x sub 0 ay malapit na dun sa root. Okay? Now, how malapit is malapit? Alright, yun yung question. Kasi hindi binigay ng Theorem 3.1 yung delta. Oh, by the way, yung proof ng Theorem 3.1, babalikan na lang natin when we learn the general theory of fixed point iterations. So, but for now, let's believe that Theorem 3.1 is true. All right. Okay, so let's analyze yung theorem para tingnan natin baka magkaroon tayo ng idea paano pipiliin si delta or paano makikita si delta because that will tell us gaano dapat kalayo. Okay? Or at least maabisuhan tayo na pag ito yung function, hindi magandang gamitan yung Newton-Raphson. Maybe we can find some criteria in one form or another para masabi para masabi na magandang gamitan yung Newton-Raphson method. Okay? And let's do that. And we'll start with this very classical result, okay, equation 3.6. This gives us the Taylor series expansion of the function f within a neighborhood of x sub n. So ito yung ginawa niyo sa matter T, Taylor series expansion. Pero tinrancate ko na siya, tapos gumamit ako ng mean value theorem para makuha ko yung c sub n, yung number c sub n, between r and x sub n. Para hindi ko na kailangan kunin yung infinite number of terms. Okay? So yan yung Taylor series expansion. Equal to kasi yun nga, yung error term dito ay naka f double prime. And mean value theorem na ginawa natin sa 174 told us na pwede mong palitan yung or evaluate na lamang yung yung nth order derivative kung saan mo puputulin yung expansion in a number between r and x sub n. Kaya nagkaroon dito ng c. Hindi natin alam kung sino si c sub n, pero alam natin it's just a number between r and x sub n. So ito yung expansion niya. Okay? Taylor series expansion ni f. And then we already know that at r, the function value is 0. Si r ay root. So pwede kong gamitin yung info na yon. And also, recall na by how we define the Newton-Raphson method, yung x sub n minus x sub n plus 1 ay equals sa f of x sub n over f prime of x sub n. So nanggaling siya sa equation 3.2. Okay? We just solve for x sub n plus 1 minus x sub n. Okay? So may negative sign siya dapat. Sana hindi ko siya nakalimutan. Okay. May negative sign siya kasi minultiply ko both sides by negative na, right? It should have been x sub n plus 1 minus x sub n equals negative of f of x sub n over f prime of x sub n. So everything multiplied by negative 1. So ito yung ingredients na gagamitin ko sa equation 3.6. So una, gawin kong 0 yung right-hand side. I just copied over the right-hand side. And then what I'll do, since we know that f prime of r is not equal to 0, okay? So I'm hoping that f of x sub n will also not be equal to 0, okay? Sinulat ko ba siya? Kasi magiging undefined yung iteration kapag ka yung yung derivative ng function ay nag-zero dun sa mga x sub n's. So it's a reasonable assumption that f prime of x sub n's will not be equal to 0. Otherwise, automatic na hindi na mag-work yung method. Okay? So what I'll do is to divide both sides by the derivative of f evaluated at x sub n. So dinivide ko to, so na-cancel to, tapos nagkaroon siya nun sa ilalim. All right, so pure algebra so far. And then look at this term. This is exactly x sub n minus x sub n plus 1. All right, ito yung ninote ko kanina. So this guy was replaced by this guy. All right, and then everything is just copied over. And then x sub n here minus x sub n here. Magzi-zero yan. So magkakaroon ka ng r minus x sub n plus 1. And then solve for r minus x sub n, we'll get this guy after rearranging some terms. Okay. So let's see what does this last equation tells us, right? Ang sinasabi niya ay yung r minus x sub n, but what is r minus x sub n? This is the error on the n plus 1 iteration, right? R is the actual root. X sub n plus 1 is our n plus 1 estimate. So ito yung error dun sa n plus 1 step ng iteration. And this equation is telling us that this is equal to this constant, all right? F double prime of C sub n is just a constant. Di natin alam yung value, pero we know it's just a constant. 2 over F prime evaluated at x sub n, that's another constant, all right? Times r minus x sub n squared. So this means you can treat this as a constant m, okay? Yung error on the n plus 1 step is a constant times the square of the error from the previous estimate. Okay? So that means this means that the Newton Raphson method has a quadratic order of convergence, right? Kasi pag kinuha mo yung limit ng r minus x sub n plus 1 over r minus x sub n quantity squared, as n approaches positive infinity, this is estimated well by x minus, sige, hindi ko nasusulat yung estimated well. Ito ay equal sa isang constant, right? This constant over here. So if you will compare this with the definition of our rate of convergence, it will be very similar, all right? So it is the current error divided by the square of the error equal to a constant, and this is hopefully greater than 0, okay? So if this is greater than 0, then indeed Newton Raphson will converge quadratically, okay? So kaya mas mabilis siya kaysa dun sa kaysa dun sa mga interval-based methods, the bisection and the regular falsy methods, okay? Now, how can we guarantee na magko-converge siya? Well, kapag ka yung r minus x sub n ay mas maliit na kay 1. Okay? Because if this guy is larger than 1, then this would be larger than 1. So parang papalaki pa ng papalaki yung error, right? Because this is just bounded above by a constant. So we want that the distance between our root and x sub 0 to be smaller than 1 para makuha na natin yung quadratic convergence. Okay? Kapag ka hindi siya less than 1, ibig sabihin ay posible pa rin siya mag-converge in the long run, pero the first few steps of the Newton Raphson method will be very slow. Pero once na yung R minus X sub n ay naging mas maliit na kaysa kay 1, mas mabilis na yung convergence. Doon natin makikita yung quadratic convergence ng method. So parang staggered quadratic convergence. Especially if you choose your initial guess to be not close to 0. Not close enough to R. Close enough meaning less than 1 yung distance nila. Pero once you choose X sub 0 uh, to be within 1 unit away from the actual root, then you're fine. You will experience the quadratic convergence. Okay? Yung sa example natin kanina, sa example 3.2, greater than 1, yung distance ng x sub 0 kaysa dun sa actual root, which is around 1.13. All right? So, di ba yung x sub 0 natin sa problem number 2 ay 3. So, 1.87 approximately yung distance nila. Kaya may nadagdag na mga 4 na iterations. Kasi nga sa simula, mabagal yung convergence. Para siyang diesel. Kailangan mo nang painitin yung makina bago siya mag-quadratic convergence. All right? So that's why we really want to choose the x sub n to be very close to, or x sub 0 to be very close to the actual root. Okay? Now, kailangan pa rin natin magkaroon ng idea. Though, yeah, that's a nice characterization. X sub 0 to be much less than 1. So yung double less than, ibig sabihin niya much less than 1. Okay? Pero ano yung minimum? Ano yung maximum value nung absolute value ni R minus X sub 0 na makakagaranti sa atin ng convergence? Alright? So ano dapat yung worst case? Well, yung Newton Raphson theorem, theorem 3.1 didn't give us any idea. Pero a quick look, alright, dun sa estimates na nakukuha natin. Remember ito, tatawagin ko siya, so kinapi ko siya dyan. Tapos kapag ka si X sub n ay malapit na dun sa root, if it is sufficiently close to the root, then this guy is approximately equal to 2f prime of r. Okay? And then since c sub n is chosen to be a number between r and x sub n, all right? Tapos kung malapit na si r at saka si x sub n sa isa't isa, therefore si c sub n malapit na rin siya kay r. Kaya yung numerator pwede kong palitan ng f double prime of r. And that really makes this ratio equal to some constant. Kasi siya lang yung ratio ng f double prime evaluated at the root divided by 2 times f prime evaluated at the root. Okay, so yung error estimate natin, with this idea in mind, so ito pinalitan lang ng m, alright? So magiging ito na siya. And then we multiply both sides by m para lang maipasok si m dun sa naka-raise sa power 2. Okay, we'll get this. And then if we will assume na nandun na tayo sa kalagitnaan ng iteration, meaning r minus x sub n is smaller than 1, okay? Pwede na nating masabi via induction that this is true. Well, kasi ito, pwede ko itong masulat na m times r minus x sub n. Paano ko nga ito ginawa by induction? Okay. So remember yung r minus x sub n, pwede ko siyang isulat na r minus x sub n minus 1 quantity squared. Okay, tapos naka-square pa to. Remember yung error dun sa n plus 1 iterate ay constant times yung error dun sa nth iterate squared. So yung error r minus x sub n is the square of the error in the nth minus 1 iterate. Kaya meron diyang square. So magiging ito na siya. So meron pang m dito kasi nga m times nga pala yon. So this will be m squared times r minus x sub n minus 1. Pwede ko na palang ilabas yung square din. Magiging to the fourth na siya. Okay. Tapos you can do this repetitively. So magiging ano naman siya, m times r minus x sub n minus 2 raised to the 6th power and so on. So you can do this process repetitively and you will get this estimate. Kaya naging power 2 to the n etong nasa taas. All right? And then we can solve for r minus x sub 0 and see that that is less than 1 over m. Okay. Kasi nga ito ay equal lang kay m to the 2n times r minus x sub 0 raised to the 2n. Okay. So, ano nangyari? Hindi ko pala siya sinolve. Ano nangyari dito? Let's see. Okay, this guy is true. And then the goal is for x sub n to approach r. If we want x sub n to approach r, then we want this guy to be less than 1. And that kind of that makes sense because if this value, okay, kung itong value na to ay hindi less than 1, so ibig sabihin yung error palaki ng palaki. All right? If this one, the one inside 2 to the power n, yung m times r minus x of 0, kapag ka greater than 1 yan, pag ni-raise mo kay 2 to the n, mas lumalaki yung value, right? Especially for large n's. So we want this guy or the base of that guy to be less than 1. Para mag-approach ng 0 mabilis yung something raised to the 2n. And then this is the simpler inequality that we need to work out. So r minus x sub 0 must be less than 1 over the magnitude of m. Okay? So ano ibig sabihin niya? Dapat pala para mag-converge quadratically yung Newton Raphson method, dapat yung x sub 0 natin, piliin natin na malapit kay r at ano yung bound para doon, ano yung pinakamalaking distansya na pwede nating payagan between them. That's 1 over the magnitude of m. But what is 1 over the magnitude of m? That is 2f prime of r over f double prime of r. Okay? Which is still a problem because we really don't know what the value of r, what is the value of r. Okay? Kasi nga yun yung root nating hinahanap. Pero if you can compute the derivative and the second derivative of the function, then you can find upper bounds for them. Pwede kang kumuha ng upper bound para kay f prime, lower bound para kay f double prime para makuha yung maximum value ni 1 over magnitude of m. Now, if the magnitude of m is large, then x sub 0 must be chosen to be very close to r. Okay? Kasi pag malaki si m, ibig sabihin yung 1 over magnitude ni m ay maliit na number. So yung distance between r and x sub 0 should be very small. So that would be a very huge problem. However, if m is small, then we can kind of relax kasi medyo kahit malayong x sub 0 posible. All right? So ano nga ba yung value na nire-represent nitong ratio na to? F prime actually tells us about the rate of growth of the function. So gusto natin dapat maliit yung gusto natin malaki yung value na to. So posible pala na malaki yung rate of growth pero dapat yung concavity ng function ay maliit. Yung second derivative kasi nagsasabi sa atin gaano ka concave yung function natin. So if your function has a high growth rate, all right, mabilis siyang lumalaki, okay lang siya as long as dapat mababa yung concavity niya. Pero kung malaki yung concavity ng function and at the same time mabilis yung rate of growth niya, medyo mahihirapan tayong gamitin si Newton Raphson. All right? Now, okay, maybe I can stop here. Sorry, 4 minutes over time na pala ako. But do you guys have any questions about the Newton Raphson method? After pag-usapan natin yung exercise for Monday. Any questions muna about the method? Sorry kung medyo masyadong mabilis yung analysis. You can read the module again if you want to revisit the analysis that I just discussed with you. All right? Kung kailangan niyo ng more time para i-absorb yung mga pinagsasabi ko kanina. Pwede niyong basahin kasi kung ano yung script na sinasabi ko sa klase, yun yung nakasulat dyan. Kasi Sinulat ko siya from scratch. So yung ideas ko, siya rin yung nakasulat dyan. So, yeah. Okay, so if there are no questions at kung gusto, inaan nyo pa siya, inaabsorb nyo pa. Okay. Punta ko mabilis yung problem. Okay. Dun sa exercise 1.2, it's the same problem as last week. So parehas yung function. Kaya lang sa Newton Raphson, kailangan niyo yung derivative ng f, right? Yun yung a little drawback behind it. Kailangan natin computin si f prime. Pero madali naman computin yung f prime kasi it's a function of r. So it's just a power function. Gagamit lang kayo ng power law sa differentiation. So that should be fine. The deadline is 11:59, so don't worry about that. Okay. Same problem as before. Same din yung hinahanap. Okay. Kaya lang, mababago lang dito ay yung kailangan nyo ng starting point. Pipili kayo on this interval, Newton Raphson Method. Tapos jump-based yung tolerance. Hindi ko pa yata kayo pinagawa ng jump-based tolerance. So start writing the jump-based tolerance stopping criterion kasi siya yung recommended sa Newton Raphson. Okay? So yun yung gagawin nyo dito. Okay? And if you can, please put the amount of time needed to complete the simulation. Okay? If possible. Pero kung hindi kaya, pwedeng hindi nyo na ilagay. Sa MATLAB kasi pwede ka maglagay ng tick dun sa simula ng program, bago yung program mo. Tapos talk dun sa dulo. I-output niya yung time elapsed, kung ilang seconds yung haba ng iteration. So ito yung program proper. Pero siguro, I don't know sa Python kung ganun din kadali o kung Excel pala mahirap, no? Kasi hindi nyo mata-time. So siguro tanggalin ko na lang yung points sa amount of time. But it will be great if you can take note of that. If you're using MATLAB or Python, pwede nyo i-time yung program. It would be nice to see that. Okay. So pwede nyo gawin yung 1A. That's fine. 1B ay hindi pa. Secant method siya. Yung number 2 hindi. So yung part 1, 1.2a ay 1a lamang. Ito ay problem 1a lang. So, yun yung mga kailangan nyo sagutan. So, ang kailangan i-submit sa Monday ay 1.1 part B, which will consists of problems 4 and 5 nga ba? Sorry, nakalimutan ko. Yung last two problems from the previous exercise, basta hindi nyo pa nasagutan sa previous exercise. And then another PDF file for and another submission bin for for laboratory exercise 1.2 part A. Ang laman niya lang yung problem 1A, yung Newton Raphson method. Okay? So, any questions? Thank you, Michael. 5 and 6 daw yung hindi pa nasasagutan. So problems 5 and 6 from lab exercise 1.1, that will constitute 1.1b. Tapos problem 1a from 1.2 will comprise lab exer 1.2 part A. Okay? So, yeah. Tapos siguro we'll need both meetings next week to finish module number 3. So, try kong i-upload yung module number 4. Sinusulat ko pa siya probably by middle of next week na lang. Pero hindi pa naman natin siya kailangan because I think we still need 2 meetings to finish module 3. Okay? So other concerns? Okay, so if there are none, guys, enjoy the rest of the day. Have a good weekend and let's see each other again on Wednesday. Bye, everyone.
Thank you po, sir.